Good afternoon, everyone. My name is Sijin, and I'm a senior scientist at ESR. So today I'm going to present one of our AI-powered public health modeling system. For New Zealand, we call it GUNZ. It's a funny name, very strange name, but I won't get into details how we come up with that because it takes days to explain. But basically, this is a collaboration effort from multiple teams at ESR, from data science, public health, and the social science system, and lots of international partners from the UK and the US. And so GUNZ is essentially an integrated modeling system connecting the communicable diseases database. Currently, we are managing at ESR, and an agent-based model, if you know what is an agent-based model, and the latest AI technology. And we're trying to couple all of these components together to provide better infectious diseases risk prediction and assessment. And as I mentioned, currently we're developing this modeling framework mainly for infectious diseases. So if you're familiar with infectious diseases models, there are two traditional models. One is compartment models, and another one is agent-based model. So what GUNZ does is that it's kind of like take advantage of all of these traditional models, put them together, and thanks for some of the latest AI technology we are using. And this is one of these tables published by, I think it's MIT and Oxford last year or 2 years ago. So when we talk about AI, what exactly we are using? So in this model, we actually couple two kind of like an AI technology together. One is LSTM, long short-term memory, and another is graph neural network. So we use, I will talk about this one a little bit more later, but we use graph neural network to actually simulate the social dynamics, and we use LSTM to simulate the temporal involved parameters in our model. And one of the things I quite like for this model is that for a traditional agent-based model, for example, it takes many human hours to calibrate because there are so many parameters. But because currently we're using deep learning, most of these parameters actually can be automatically calibrated. And another thing is that because all the agents or individuals in the model is vectorized, so basically we can use GPUs. So we use this model and pass it to some of our international partners, and they use it for the COVID outbreak in London. And traditionally it takes 900 CPU hours to run one simulation, and now it reduced to 40 seconds with GPU. And so what's a core modeling capability? And probably you're familiar with agent-based model. Essentially, it starts from a single person. That single person is just like a real person, like all of us. We have age, we have gender, and we have our income. We have a bunch of attributes. We have our health background, and we actually interact with each other. So in our model, we have 5 million individuals and living and working and playing together. And so this is essentially a bottom-up approach. Essentially, we're trying to simulate individual behaviors and derive the social behavior so we can actually investigate, for example, different policies for different social settings, different areas, different ethnicities, and so on. And one of these foundations for this model is a New Zealand synthetic population. It's a very large population data set we created through this project. It contains 5 million plus individuals for New Zealand. And each individual, as I mentioned, just like an individual, like any of us. We work together, and probably in the model now, some of them are attending an AI conference somewhere in Auckland, I don't know. And we have this very large data set, and they are very well validated against many census and surveys in New Zealand, and the reports are publicly available. For example, in this figure, it just shows people living in one apartment, how they go to work, I think at 7 a.m. in the morning or something like that, or how people interact within a particular school. And we use this, as I mentioned, use this model to actually try to simulate infectious diseases. For example, this is just to investigate how we actually should put the target vaccination campaign for a particular area of particular ethnicity. And this is last slide, and this model is semi-operationalized, and we have used this model to support lots of like initiatives in the public health agency and so on. And we're actively looking for collaborators, and feel free to talk to me after this meeting. Thank you.
Thank you. Welcome, everyone. Thanks for still being here. So I'm Bernhard Pfahringer, and I'm from the University of Waikato, and we have this research institute. Not a center, just an institute, but it's also good. Kind of just want to talk a little bit about the current research that's happening there in terms of two themes that we've been looking at for a long time, and what we're currently doing and where we're trying to go, and maybe interest you in some of that. So it said streamlining and it said continual learning. So I have one slide just about streamlining. You have heard about streaming from Albert before, and it was mentioned somewhat more than that. But just to remind you, most machine learning, we have this assumption that we have a bunch of training data, and we have some test data in the future, and we assume that the distributions are the same in test and train, and then we have arbitrary amounts of compute to get a good model on the training data, and then hopefully we get good predictions. In the real world, that IID assumption never holds. It might hold for a little bit of time, approximately, but in the long run it never does. And machine learning is still successful because companies regularly retrain models. And you can read about that. Different companies are pretty open about it, like the house value estimation, they redo that every week. If you look at Facebook, they have different things, but some things are being done like multiple times a day, some things are only done once a month. But you retrain. Now, stream learning is kind of the idea to get away from this and be online all the time and adapt to the data as it changes. So you need an incremental algorithm, you need have strong limitations on your computing resources in terms of memory and compute, but you also are able to predict at any given time, so you're an anytime classifier. And if the data is static, then hopefully you get the same result, but if the data changes, hopefully you perform better without having to explicitly retrain. And that has been around for a while. Albert mentioned the textbook and stuff like that. And this is, if you look at what happens in streamlining, it's mainly classical machine learning. You find trees and forests and stuff like that. And in the neural network community, there has been a similar trend for starting maybe in the mid-1990s. They have a different name for it. It's called continual learning. It was actually called lifelong learning before. And this is a definition from their webpage. So there's a webpage papers with code about continual learning. And they have a lot of other stuff as well, but the sub-webpage for continual learning has an explicit definition, which is kind of cool because we've heard today that there's a lot of things that are not being defined. Here we have a definition. And it's pretty active. These numbers that I put you there, they change every few weeks or every few days, actually, the number of papers. Maybe the data sets and benchmarks don't go up there quickly. So with this continual learning, the main assumption is you have different tasks that are somehow connected to each other, and you learn them one after the other. And there's different versions where you have to be explicitly told, not just this is a new task, but also what is the identity, or this is this task and this is that task, and that may be needed for training and for testing. And the difference is maybe that you add new classes, so you change the Y, the targets, or that you modify your representation, the input, the X, like a very high quality image and a really noisy image here on the right. But these are kind of just some subgroups. The interesting thing is, how do we evaluate that? So it's not just the accuracy that you're interested in, and usually the accuracy is an average accuracy across all the tasks, but also how much do you forget? You have trained on a new task, can you still do very well on the old task, or have you completely forgotten, or is there some intermediate? And then, does your knowledge transfer in both directions, like with the new task? Can I now do better on the old task as well because I've excelled at the new task? And the other way around. There's basically three groups of methods for continual learning. One's based on regularization. So basically the idea is that you prevent your network from making big changes because you're worrying that that might lead to forgetting. There's this term catastrophic forgetting, and we can see that. And then there's replay, where you keep some of the old data and replay again and again. And then there's this idea of maybe we have a big network and parts of it are for that task and parts are for that task and some overlap. And maybe we can actually grow and add some stuff as well over time. Now, online continual learning tries to make that a smooth process without specific task boundaries. We've published some interesting stuff, I claim interesting stuff at NeurIPS 2 years ago, and the newer work is all under review and being rejected and being rewritten and stuff like that. But basically what we've shown is that with replay you can do really well if you use strong augmentation and multiple iterations on the replay. And this is just basically a summary. So both kind of have the same problem that they address, but they have different purposes. Stream learning just wants to be good now, on what we have now. Online continual learning wants to be good now and for the past. And, well, there's different methods, and I think there's quite a bit of potential overlap. So what we're looking at is maybe having a generic framework that can capture various different things around streaming data, which then will also include reinforcement learning, time series prediction, and active learning. And that's it. Thank you.
Thank you everyone for still being around, and thank you for the organizers for putting this together. This has been a wonderful day so far, a lot of ideas, a lot of connections. Thank you. So I'm Yuqian from mechanical engineering. I'm not an AI researcher. I was educated with a mechanical background, but then went to the wild world, worked a number of years as software developer, and now working at University of Auckland doing applied AI research, if you call that, or AI engineering, probably more accurate. But what excites us is really see advanced AI technologies making impact in real world. And by my working experience in real world, as well as current collaborations with a number of companies, we see that the excitement is really there. But what they don't know a lot is that, hey, what does AI do, or what is AI as a first question? So we see a number of work that are really exciting us. So today I would like to just highlight some of the interesting problems that we're working on, then really calling for collaborations from AI research community. So one of the very first questions that we actually working on is production scheduling, which is conventional problem. If you look at that, Professor Zhang's team has been doing amazing thing in the world. And we look at this production scheduling from a New Zealand factories perspective. You find that, hey, why there are so many published papers there, but actually factory scheduling solutions hasn't been that advanced, or why not taking uptake that? So talked with a number of companies, talked with factory scheduling software suppliers as well. We found that, hey, actually in factories, they need scheduling decisions being made kind of whenever they want. Okay, because there's always demands coming, always new jobs coming, and you cannot predict that. And then what do? Do you run your scheduling algorithm again and disrupt the current schedule that already into production, or you take care of all these uncertainties? So really, it's a very hard decision to make. So what we found actually scheduling problem in real world is more challenging than was defined in the literature, flexible job scheduling. For example, as a production engineer, I'm really caring about my factory performance on a continuous time horizon, not just one-off scheduling, right? So if you look at the heuristic algorithm out there, maybe they work really well on those benchmarked data set, but how about you apply them into the real world? Can you deal with a variety of jobs, unpredictable urgent job arrivals, or continuous kind of performance over time horizon? So we're really asking ourselves these questions, and it turns out that can be great collaboration that can be there. So luckily we work with Aaron Chen from University of Wellington, computer scientist, as well as our talented PhD student who actually has a joint degree between computer science and engineering. Wonderful. So we formulate this problem here, as well as then we look for solutions. We actually found that possibly we can model the whole system and multi-agent systems, then really leverage the capability of reinforcement learning there to really see, can we actually train a generic policy that can do scheduling from one factory, then can tailor to another factory without a lot of the retraining or without retraining at all. So we look at all these things together with domain experts, with computer scientists, and really redefining the problem that we have to solve in this field, as well as really look for fundamental science there and work together. So this is just an example of what we are doing. But if you look at what other areas that our team is working on, so the problem that I just mentioned, dynamic continuous scheduling, is just part of the self-organizing manufacturing vision that we have. So imagine in the future, factories can actually be autonomous, so that machines have its own intelligence, can do whatever they like, but they work together nicely. So that's what we call self-organizing manufacturing. Another area we look at is human-robot collaboration. There's a lot of fantastic research problems there that we really working together, from really capturing human emotions from a real-time perspective to understanding emotions as well, right? Digital twin research, we worked a lot on digital twin, but machine learning can really make a difference there. How can you make digital twin more accurate, more responsive in real time, and lighter as well if you want to deploy outdoor out there. And on the right-hand side, I put knowledge engineering there. So from an engineering perspective, we see lots of needs of harnessing the data from technical drawings, from your 3D models, from maintenance manuals, all of that. Can you really look at this multimodality data from there and then harness the data, knowledge from there, then make decisions. So as example, we actually did some work, create an open source data set targeting the assembly area. That luckily we found that, hey, all these foundational techniques that people talk about, action segmentation, recognition, all of that actually not working so well for real world problems. So luckily we invited to NIWA 2023 last year, present our work. This is an overview of the data set of 1 year's efforts actually created to really understand what's the complex research challenges out there in assembly area in real world manufacturing. So with all of that, I'd like to show a number of videos that with the active research we're working on, really calling for collaborations together. For example, the bottom left is a research funded by Safety and made to One News, talking about how to make robots in the cloud, and work together with Nokia, Spark together, really see how machine learning can make impact. So with all that, thank you very much.
Kia ora koutou. I'd just like to talk to you about the regulation of AI, and of course AI is a broad word, but I think it's probably of interest to all of you, or most of you that are developing it, because it is progressing, and I just thought it might be interesting to look at what different jurisdictions were doing, and I call them three major players. So the US, the EU, and China. And of course I can't speak Chinese, I can speak French, but I can't speak Chinese, so I had to use secondary sources on that. I can't swear that that's accurate, but it's accurate enough. Anyway, what was interesting to me, well, in the US it's a hodgepodge. There's the federal, President Biden did an executive order in October of 23 that's pretty much aimed at protective stuff. And I see a lot of the regulation in the states at the federal level is aimed at keeping the technology, control of the technology in the country, but not controlling what the technology does. Yeah, that's at the federal level. At the state level, at the federal legislative level, it's a mess right now, as I'm sure you're aware. They're not doing much. And then at the state level, there's, I think it's 16 states that have legislated, and most of their legislation is aimed at avoiding discrimination, applications of AI that are discriminative, but it's all a little hodgepodge. The EU's done a comprehensive thing, and they've come up with a thing of 3 levels: prohibited, risky, and pretty much non-regulated. And then China's ahead of the game. It started regulating earlier. And I thought it was interesting to try and look at what was shared and contrasting underlying concerns. So security was one that everybody had, but for different things. Shared, everybody's worried about finances and infrastructure and national security. Not everybody is worried about personal information. Political process and elections, it tends to depend on whether you're a democratic jurisdiction or not. most everybody was worried about commercial applications and fairness as well as commercial secrets, competitive advantage. And what was interesting is some jurisdictions are worried about AI and biosecurity and using AI to do genetic engineering in bad ways, or even down to, like, you know, acids and things like that. Discrimination was big in the EU and in the States. What I thought was interesting was in China you had a right for a reason, transparency. If an AI program made a decision that affected you, you had a right to be given the why, maybe not change it or anything, but a why. What was interesting is also information oversight. Some jurisdictions were worried about misinformation, disinformation, and making sure information was factual. Other jurisdictions were more worried about managing information such that it enhanced social cohesion, whereas other jurisdictions like the EU and the US were worried about not information that enhanced social cohesion, but preventing information that was not true, and they didn't care if the true information enhanced social cohesion or not. But in China, there's an affirmative duty to algorithms and things, and generative AI, to do things in a way that enhances social cohesion, which I thought was interesting, and maybe we ought to think about that. Privacy and liberties concerns were the democratic jurisdictions. Commercial advantage, that was pretty much everybody. What I also thought was interesting is in China you had regulations about not using AI for unfair competition, unfair pricing against people, and remedies for harm, which I thought was what we ought to worry about here, is because what's going to happen is people are going to be liable for their creations. And most regulation is of the preventative nature, trying to make people create things that don't do harm, but also there's traditional liability for harmful creations and liability for harm. And there's kind of a debate in the legal community about should you use existing legal frameworks and adapt them to AI, or do you create a whole new legal ecosystem for AI? And kind of what there is, and what I think there will develop, is, I call it level 0. Non-generative AI would probably be along the lines of environmental regulation, preventative things, regulations about what you can and cannot do when you're making this. Generative or what I call semi-independent AI, where the AI can do things that are surprising and not foreseen. Well, we could model that on animal law, and what's interesting is we also now have precedent where parents have been done for manslaughter for the actions of their children, which children were deemed able to be tried as adults, okay? Minor children, but old enough to be tried as adults. Yep, okay, I'm almost done. And that models animal law, where if you have something that can act independently and you don't control it, you're liable. It's interesting maybe for you guys to know that you could be liable up through manslaughter. And level 2 is when it's an independent actor and it can create its own AI, and then that would be like what we would call maybe true thinking minds. And that's the end. The fundamental questions are, how do you achieve precautionary and protective regulatory goals without stifling a jurisdiction's competitive advantage? The EU has created what they call regulatory sandboxes, where people can go in a supervised manner and do things outside the regulations to test to see if it hurts anything or not. At what level does AI become morally considerate? And that's that thing about defining what is, do you need life to be morally considerate? Do we are we prejudiced for the biological when you define what is life? Does it have to be biological, or is it the mind that makes it alive? And should we start integrating those kind of things into our regulatory approaches right now?
Thank you, everyone. My name is Ime, and I'm from Center for Data Science and Artificial Intelligence from University of Wellington, the same as Mong, Bin, Qi, and Fangfang, and also Annie there. So we have a group working on using machine learning for combinatorial optimization. So it's good to see a number of talks also working on similar problems. So today, I'm going to just introduce an example of the problem that we recently worked on and that excited us. So that's called emergency medical dispatch. Basically, that's to dispatch ambulances to emergency calls, and we're collaborating with the Wellington Free Ambulance. We visited their office, and you can see, the dispatching is very hard, and you need to deal with many calls that happen in real time, and the dispatchers actually need to decide, okay, how many ambulances are out there and where they are, and how to dispatch all these ambulances, and also the staff in the ambulance to satisfy all these requirements. And the challenge is mainly, a lot of challenges, but particularly this highly dynamic environment, because you always have new calls that you don't know. And the uncertainty, basically when you get a call, you don't know how serious they are. And also the interactions between them. So this is a very basic illustration of how this is dispatched. So you get a call, you have all these ambulances distributed, and then you allocate, multiple ambulances to multiple calls at the same time. So this, we call this emergency medical dispatch decisions, and you have a number of decisions that you need to make. They are all interacting with each other and make the decision very hard. And we can model this process as a Markov decision process. Just skip because of the time. So we have the state, about the locations of the ambulance and the calls, and then we use this so-called rule to match that. So this is what the way we solve the problem. But this rule, EMD rule, is the key for the problem solving. Firstly, how do we represent? We use a priority function to represent this rule. Basically, if you have emergency, if you have an ambulance, then we have a priority here. This is what the rule generates given this pair. And that rule can be, a combination of many features. And then, for example, we get these priority values, and based on the priority value, we select, okay, emergency 2 will be this ambulance. And then we use machine learning to learn this rule, and we use a tree structure. Yuqian just talked about reinforcement learning, but actually we use a different representation and method called genetic programming. And it uses this evolutionary process to learn the rule. And this rule evaluation is based on simulation. And we have the training data and we have the rule. How do we evaluate it? And we have this simulation process, and we put the training data in different steps of this simulation, and then also put the rule in to make the decisions during the simulation. And finally, we output how good this rule is. And the whole thing will be used to evaluate the rule, and then we use genetic programming to iteratively improve and search for better and better rules. And we got some results, and for different scenarios we test and we compare with the way that those Wellington Free Ambulance, their dispatchers are actually using. On some scenarios we can get a huge improvement. And we also made a demo, and we compared the baseline which is being used, and then how we use machine learning to learn the policy. And then this is some difference that you can see the decision is different. And we also we do this project collaborating with William Free. We got a smart idea last year, and we also got a award, basically. Sorry. Yeah, I'm finishing. Yeah, so for an international conference in our field, that we actually win the award due to the human competitive results for the real world application. And in the future, we also have a lot, these challenges that we're going to deal with, and we are also expanding our techniques to other applications. For example, with TransDev, that we're trying to help them with their railway network. Oh, by the way, we also try to compare with reinforcement learning, and our experience tells at least, we are not worse than, and we also have a number of advantages there. Yeah, finally, thank you. Thank all my colleagues and the research group. Yeah, that's all. Thank you.
Thanks.
So imagine you're in your Tesla, in its semi-autonomous vehicle mode. And then it can brake and accelerate, but then you hit a pothole and you rack up a $2,000 bill on your wheels, right? Also, city councils are liable for road maintenance as well. Like if they have noticed a fault and not repairing a fixed period of time, they could be liable for that bill. So the project we're working on is on-vehicle real-time image connection, and also enable real-time pavement defect identification as well. So that's our goal. My name is Thomas. I lead the UC cell group, and we have two research associates, Zach and Ming. Click here. So this project is in collaboration with City Council and Waikato and the ETA. And we use like a variety of deep learning research application tools. And we also have 3 full-time research students. And we have collected over 3,000 kilometer road data using the tools that we have, and over 400 cases of funding for this project. So. At the start, our research group started by doing a lot of image processing. So that's not related to this project, where we can merge image together and do 2D LiDAR processing and so on. That's some of the capabilities our research have. And in 2020, we started collect data, first by identifying the road surface first. So this is a relatively easy project. We just did thousands of images and getting a good accuracy of the road surface first. Okay, coming to the main part of the project is to set up a camera system that can connect with a processing device and able to do each processing. So there's a few things that need to be done. Firstly, the data needs to be able to dump automatically over Wi-Fi connections when vehicles return to base, and the processing and filtering need to happen in real time. So here is the overall data pipeline that we use for the proof of concept. So we have sensors that talk with each computers. So each computer dictates when the sensors take data, and each computer also process the image. I'll give you some examples. And then it will flag out which image potentially have a road defect, and this is mounted on a street sweeper vehicles. We use a street sweeper because they drive at 20 kilometers an hour rather than 50, so just for proof of concept. So we collected over 100,000 images, and then we did some results. So first, for the sort of the high either base processing, we were able to get over 90% accuracy for classification, what sort of defect is. Potholes is the most important one because potholes is where it does most of the damage. Also, we're getting good bounding boxes. So not only with finding the defects, we're able to find an approximate size of the defects as well. And here's sort of like the confusion matrix for this. In terms of output, there's no additional human setup. Everything's automatic, so you just plug it in. When the power turns on, everything runs. When it reaches the Wi-Fi point, everything gets dumped. It's automatic collection and transfer. It's automated classification on the fly. And we have flagged about 20,000 images contains potholes are the defects, and it's over 90% accurate in terms of whether it contains defects or not. So in conclusion, we have demonstrated a quality classification and segmentation results with the setup. So over 90% classification accuracy, around 70% size estimation accuracy with the IOU. It's fully automated, and over 90% of the flagged images that's processed on the fly while the data is being collected are actual defect images. And we have achieved onboard detection. I would love to open this up for more collaborations. If there are sort of other universities and institutions, happy to work on this project together. So thank you.
Thank you. Hello everyone, my name is Guilherme. Fun fact, Guilherme is just the Portuguese for William, but it's really hard to say for English speakers. I should adopt William maybe. Today I'm a postdoc with the AI Institute, and I'm going to talk about this forecasting the longitudinal tree. This very long title, but basically it's a case study for plantation forests. To give you a brief overview or a brief context, plantation forests, general perception is not the best. I knew the ones back in my home country in Brazil. People are usually, yeah, if a plantation forest starts, everything around just gets dry. The water just vanishes. And it was a shock, maybe not a shock, but surprising to learn that New Zealand is not very different. So you can see for the headlines, this is 2022, this is 2019. So yeah, plantation forests do not have the best perception. And there's one of the collaborations we have, it's forest flows. It's, I think I had the logo here below, Sijin. So Forest Flows project tries to understand the impact in the water usage and also the downstream water supply, water quality, water quantity of the plantation forests into the hydric system. And then, yeah, they do research in forest hydrology. So this is a very nice picture of their remote sensing infrastructure. There is data from, where's my mouse? Satellites, some LiDAR, tree canopy, water stress, and then some above ground sensors, like sensors from a weather station, rainfall, truefall, tree growth, water usage, and so on. Also some below ground, which is like soil data, using the soil moisture, groundwater, and so on. In total, there's a lot of observations in this data set, and this data set spans across several different sites. They call sites each forest. And so they have this very large data set, and they try to understand how water is being used. So the goals of this collaboration project are first to forecast from streaming near real-time data. The second one is to provide some explanations on how the water is being used. I am not approaching this first goal here because of, just too short. And let's talk a little bit about the explainable AI. So this is one of the plots. This is the Ashley forest. Each small square or diamond, depending on the orientation, is a 20 by 20 plot, and inside each one of these you have several sensors. One of the most important for this current project is the dendrometer sensor, which basically measures the tree growth. And then this was a pilot experiment. We just took these 6 plots and we trained a model on them, and we tried to get some explanations on what are the driving factors for the tree growth using the occlusion method, which basically we add perturbations to the input, and we see the differences compared to the original data. Differences in the forecasted value compared to the forecasted value with original data. And here are some, just two very quick results. This one is missing a few information. This one is the minimum method, so we just set the values to the minimum of the data for each feature, and below you have the maximum. Here, that's one thing that the biologists, they were happy because relative humidity is known to be a factor linked to tree growth, and it's known to change across the weather seasons. And so this is important because the impact changes between seasons. And the other one is true fall is like a different, similar but different measure than precipitation. Precipitation is like general one, and true fall is the ones that go through the canopy and into the soil. So they were quite happy to see that the local feature is more important than the global one. But yeah, there's more investigation needed to fully explain why the precipitation is not that good. Yeah, that's just some preview of this project, and a few acknowledgements, people that contributed. I might have missed some, probably in the forest flow side, but yeah, thank you everyone that contributed, and thank you for listening.
Hello everybody, I'm Fangfang from Victoria University of Wellington. Yuqian and Yi already introduced something before, so it might be easier for me to introduce my research topic. We work on a similar topic. So today I will introduce genetic programming and machine learning for job shop scheduling. My main focus is on dynamic flexible job shop scheduling. So the task is to process a number of jobs by a set of machines. And each job have a sequence of operations. Each operation can be processed by a set of machines. So actually we need to make two decisions. The first is when a new job comes, which machine to choose to process this job or operations. Another one is when a machine becomes idle, there are a lot of operations waiting in the queue, which operation to choose to be processed next. And there are some constraints, like each machine can only process at most one operation at a time. And once we start to process one operation, we can't stop. For dynamic, so we can consider different dynamic events, like job can come over time and machine broken down. And normally people try to minimize the flow time or the tardiness. Actually want to improve the production efficiency. If we consider the job as a task and the machine as the resources, there are actually a number of real-world applications of this research. The first one is, for example, the manufacturing, the production, and also yard truck scheduling at the berth, or the flight scheduling. The resources at the airport are quite limited. How can we make a good flight schedule? Also, kind of staff scheduling at the hospital or the university. So in terms of how we handle this problem, there are probably two ways. The first is we can give a solution directly. For example, we can look at this figure. It's clear to see when, at which machine, which operation is processed. And another way is instead of give the solution directly, we can use priority rules. Actually, people are good at using rules. For example, shortest processing time first, or first come, first serve. Like you go to the lunch today, first come, first serve, right? You're just waiting there. But normally this rule is quite simple, probably not good enough. My goal is to learn comprehensive rules to replace the manual rules. How can we do this? And I actually use a hybrid heuristic approach. So hybrid heuristic approach is one approach to automatically learn this kind of rules. So why we use a hybrid heuristic approach? Actually, there are a lot of benefits come from using the rules. Let's take an example. For example, if you go to the bank, normally first come, first serve, right? You're just waiting here. With the priority rules, you don't need to consider how many people waiting here. You just based on the rules, first come, first serve. You can always have a good solution there. And it can react to dynamic environment efficiently. For example, you can look at this guy. Is looking at the watch, probably is in a hurry, he probably just go somewhere. It will not affect your solutions. And also, with rules, we can handle multiple instances. You can use in bank A and also can use in bank B, right? And its rules, people are easy to understand and also easy to implement. And the genetic programming is a good approach to learn such rules. I think some of our colleagues already mentioned before. It's an evolutionary algorithm. It's actually, you can consider in this way. At the beginning, we don't know the optimal structure of the solution. We just random generate a large population of solution. And we evaluate all the solution, and we give good solution, more opportunity to generate a solution for next generation. And along with the generation, we can get a good solution at the end. To give a simple example, like we have 3 machines here and some operation waiting here, and the job continue to come, and we can learn a routine rule and calculate the priority value of all the machine and choose the machine. And also, when a machine become idle, we can learn another rule, like a sequence rule, to prioritize all the operation and choose the one with the high priority value. Well, it's easy to see, but really hard to learn. And in my research, I also use a number of machine learning techniques. For example, feature selection to reduce the search space, and the surrogate to reduce the training time. Like it's based on the dynamic simulation, normally quite time consuming. And also work on multitask learning and so on. We also work on real-world application, like the ambulance dispatch introduced before, also yard truck scaling and tugboat scaling, and so on. Thank you.
Hi, I'm Tristan Meyers. I'm an analytical meteorologist and forecaster at NIWA. Not a data scientist, but I like to use any tool I can to make forecasting better at NIWA. And so I make a lot of forecasting tools, is basically what I do. And I'm going to be presenting operational nowcasting system for wind and solar power in New Zealand. So why are we doing this? Well, New Zealand's moving towards a majority wind and solar powered grid by the time we get to 2050. That's kind of the goal that we're going for. Right now it takes up 5% of the energy distribution. It's going to go to like 55%. Projected by 2050, but the current forecasts for the power for these two sources, wind and solar, are terrible. They cause actually millions of dollars of losses in the energy grid every single year due to inefficiencies. So that's why we're getting involved here, and we're trying to come up with a solution. Now, nowcasting, I'll break that down for you. So there's a huge spectrum of forecasting. It goes from what's happening right now, and then numerical weather prediction, which is weather models like what you see on an app on your phone. It goes up to like 7-10 days. And then subseasonal, that goes out to a month. Then you have seasonal, and then climate change projections, right? And there's skillful ways to forecast these things. There's different techniques you would use to forecast these things. If you are wanting to know what the weather is doing an hour from now, one of the best methods is look out the window, and that's persistence forecasting. But if you want to go 6 hours from now, look at a weather model. That's more accurate. So there's actually a skill gap between persistence and numerical weather forecasting, weather models, and that's what nowcasting is. There's this little skill gap here, and it's blending observations into these numerical weather models. So these are physical-based models. So how do we usually nowcast? Well, a skilled meteorologist can try to do it. You have traditional algorithms that do it, called optical flow. That's from Windy. If you use Windy, they use optical flow algorithms. And then they have deep learning approaches, which are starting to come out. Google is getting involved in this stuff, and they usually focus on things like precipitation or rainfall nowcasting on radars. But what I'm focusing on is intermittent sources of renewable energy, so wind and solar, predicting wind and solar in the time horizon between now and 12 hours ahead. That's what I really care about, because energy markets really care about that. You can get wind drop-offs, you can get cloud cover, and that totally shuts off the production of certain sources of electricity, and that means thermal power stations have to fire up, and sometimes they need lead times of 9 or even 12 hours. So that prediction window is very, very important. So we're developing this nowcasting system to combat this. What we're throwing in it, this is basically an application of an AI model. I haven't really made up any of the AI model. I'm using applications of it and testing out different methods. But what we're doing is we're using deep learning, because traditional time series forecasting algorithms like ARMA or anything like that don't quite cut the mustard here. We need a global time series model, i.e. one deep learning model that can predict multiple sites at the same time. That's key, and only recently have we been really able to do that with deep learning models. And so this is what we are doing. We're throwing in raw observations. NIWA has a whole bunch of climate stations. There's like over 300, and they're measuring temperature, wind, humidity, solar radiation. And we also have satellite data. So we have data that's looking at us all the time, taking pictures every 10 minutes. So those are your past covariates of your time series model, right? You can use those. That's your persistence if you like it. But then we're blending in numerical weather prediction, weather models. We have a high resolution numerical weather model. Top right is an example of the cloud forecast of that over New Zealand. So that's from a weather model. That's not a satellite image, which you can see the detail in there. And you can see the differences of cloud. So you have the raw observations going and also the NWP blending together into a deep learning model. And that creates a nowcast. And the bottom right is an example of a nowcast, which shows a wind drop off. And you can see it seems to be working. And how well does it work? Well, so we're trialing out a few different algorithms in time series forecasting. Time series forecasting and deep learning actually appears to be more in its infancy than a lot of other fields, so it's really dynamic. People say transformers are really good for this, so we started with transformers, in particular a temporal fusion transformer, TFT, and it did a pretty good job. So on the right-hand side there, you'll see V0, V1, V2, V3. We started with transformers, and they took a really long time to train, and we realized we got the same performance out of linear models. So that's what a tide model is. So we moved to tide models, and they're global models, and they do a good job. And I know I'm running out of time here, but the next V3 is the best that we can do, and we benchmarked it versus weather models, which is MOS there, so that's an error of a weather model, and then climatology is what you would usually expect for this time of year. There's a lot of numbers on there, so I'll just show you this one. Error over the lead time of the forecast. Blue line at the top is the traditional weather model, and the mean absolute error is on the y-axis, so you can see that it's not that skillful at the beginning of the forecast, but our operational nowcast is able to basically close that gap there, and you can see that we have successfully been able to create a nowcast, and we're in the process of deploying it for a number of sites across New Zealand at the moment. So I'll stop there.
So I represent this company called Watchful. It's previously known as Crosby Security Limited. So just to introduce myself, so I did my PhD in vascular biometrics from the University of Auckland. And prior to this role, I was a data scientist with MBIE in the Forensics and Biometrics division. So what we do here at Watchful is supporting security monitoring stations. So ideally, any camera that is installed, so there are quite a few in New Zealand, whether it's in the public sector or in the private sector, most of those are not monitored, especially in New Zealand. Whereas internationally, it is. So what we do at Watchful is to take the feeds that come in from the camera and then apply AI to get context out of whatever we are seeing through the camera, and then use that as an assistive co-pilot for making decision about what's happening in that particular environment. So moving a little bit further, these are just the key features of the product, which will just give you some basic idea of it, and we call it Monica. So whoever is basically seeing Friends from the US basically will understand why we call it Monica. It's just a term that we made up. But what I'm interested here in sharing with the AI research team here is the workflow. So as I said, this app, it's an actual product. It's in production. We monetize it. And thanks to the legal IP team for cutting down all my slides and leaving me with something very little to show, something probably AI can't do yet. So as I said, we have the input image or the input feed that comes in, and we use natural language processing on that image to get some context. And then we feed in external information such as the schedules, like for example, the site is armed between say 12 midnight to morning 6 a.m. or something of that sort, and special instructions like if there's a garbage truck that comes in during that time needs to be ignored. So all of these information is basically plugged into the model, and the model is able to make some context out of it, and that helps in the decision-making process. So keeping it really simple, this is just a screenshot from the actual software where you have a site, and the site basically has, this is what a monitoring officer sees, and whenever there's an incoming alert, the alert basically is picked up by Monica, and Monica is able to basically tell you if the event is an intrusion event or a false positive. Now, the question is, why are we doing this, and why is it relevant to the AI research? Primarily because this is a direct application. This is where we want to know how this can be applied for other applications as well, other than just out of security monitoring. Because we plug this into a workflow. So for example, if the incoming event is potentially an intrusion event, then it plugs it, the entire system just changes to, okay, call the police and call the next line of action that needs to be happening. So it reduces the false positive, that's one thing, and most importantly, enables a person, like one monitor currently can look at a video wall of say 20 cameras, but having the software in place basically enables the same monitor to monitor say 5,000 cameras. So that's one of the key features here. So open to any suggestions, any of the input from the AI researchers here in this application, and with that I'll conclude my presentation.
So, good evening. Now that it's autumn and we are soon heading into the winter, it's a great time to talk about respiratory illness, right? So my name is Steffen, I'm a research fellow at the School of Computer Science here in Auckland, and I will talk about forecasting the hospitalization burden in Auckland caused by SARI. And SARI are severe acute respiratory infections. But before talking a bit about SARI, first introducing the project. So this is a large project, it's called SHIVERS, abbreviating Southern Hemisphere Influenza and Vaccine Effectiveness Research and Surveillance. Quite a long title, right? It's a collaborative project, a lot of institutions are involved here. The two big hospitals in Auckland gather a lot of data, the one in Middlemore and the city hospital just across the street. And ESR is involved. IMAG is taking care of the vaccination data, and as you can see also a lot of universities spread over New Zealand. And there's a lot about surveillance, obviously, a lot of data collection, active surveillance, for example, in Wellington, where they really kind of monitor families participating in this study, so they also track cases that are asymptotic, so they get infected, but they might never realize it. Primary care and healthline covering cases that feel bad enough to see a GP or call the healthline, and we are focusing on hospitalization. So this is SARI, tracked since 2012, and these are cases that stay in the hospital at least for a night, and they have a fever and a cough, and the onset of these symptoms has to be within the last 10 days. So this is a clear definition from the World Health Organization, actually. And what we also have for this data set is a consistent lab component, as we call it. So they test for 10 different respiratory viruses, including influenza. So the question is, can we forecast these hospitalization cases? Because they are a big thing during the winter, and this would help the hospitals here in Auckland because they might schedule elective surgeries in a different way when they know that these numbers increase a lot during the next 2 weeks or 3 weeks, for example. So one of the central questions was having this lab component, telling us basically which viruses circulate at the moment. Does this information help us to do a better prediction of SARI cases in 2 weeks, for example? And the answer, very simple here, is it's actually not really helping a lot. So when you, especially when you look at the 7-day, 14-day forecasting, when you take the univariate model, only SARI time series, it's not really improving when you add the lab component, abbreviated by LC. Interestingly, adding other time series such as Sari split into different age groups even makes it worse, right? When you look at the mean absolute percentage error. So this is interesting, and we're wondering why is that? And there's actually an explanation about explanation coming from the epidemiologists who say there's a lot of year-to-year variability. So you might sometimes have an RSV year or a strong flu year. And so we thought about maybe it helps to use smaller models that focus on really just the last flu year we had when we head into the next strong flu year. So this is the work about trying to use ensembles to improve the forecasting, trying to extract patterns from the lab component to make forecasting better. But to cut a long story short, this is work in progress. Yeah. At the moment, it looks like it's hard to beat that transformer actually, as you see here. It's actually the same one that was mentioned a few minutes ago, the temporal fusion transformer. And yeah, as I said, I will skip that slide about the ensemble idea. It's work in progress, and a few acknowledgements thanks to the supervisors and initiators of this project, Jill, Cameron, Pat and Jörg, and thanks to a lot of people from the school and the collaborators, and thanks to the Flu Lab, of course, who's funding this. And what I actually forgot here is also a lot of computation was done on the high performance computing clusters from NESI. Yeah. And yeah, thanks for your attention. And